Hi, friends of the sun. Welcome to our weekly reading group happening every Monday. And you can join us just on Zoom, or you can join on Slack. Suggest what papers you want us to cover, and all of the information is down in the description. And yeah, if you want to join, then you can have a taste of what we do non-live in the following video, where we will be talking about approximate equivariance, and I think that's like also approximate piecewise equivariance, right? And I think piecewise equivariance is especially like a concept that is quite important. Also, if we like don't really know what the pieces would be, or what the local neighborhoods where we want to be equivariant would be, and maybe has been somewhat overlooked a little bit. So let's go.
Okay, so hello everyone, and I'll be talking about a work named approximately piecewise-E equivariant networks. It's a joint work with Joey, Francis, and O. We are all part of NVIDIA research group, and let's get started. So I'll start a bit with motivation and kind of sets kind of the maybe kind of the grounds for what we're going to talk about. And so what we want to do here is we want to improve the generalization capacity, mostly in tasks that involve 3D inputs, and especially inputs where you kind of imagine complex inputs, like complex scenes that kind of comprise of, let's say, multiple objects. And moreover, we're kind of interested in settings where we operate on real world data. In a sense, in real world problem, let's say the availability of supervised labeled data is limited, and so we still want to work in this type of regimes. And just as a side note, let's say if you think about, let's say, the common approach for handling limited supervised data is usually either, maybe extract, nowadays, I don't know, maybe utilize some large foundation models, but let's leave that aside. But let's say a popular approach is just use synthetic data. Okay, so that's kind of a reference that you can have in mind for all this approach. So this kind of an example. Okay, so imagine like this is a complex scene comprises of multiple objects, and kind of, let's say, we can consider the segmentation task, which we denoted here with the different colors. But our approach is gonna build on, as I understand from the audience that you're quite familiar with, is basically exploit symmetries that are presented in the data and exploit it in a way that is gonna be incorporated into the architecture of the design of a neural network. And here again, the focus would be on symmetry that's kind of presented in complex scenes. So let's just give a simple example or two examples to understand what kind of what do I mean by symmetry exhibited in complex scenes. So for that, let's consider again some invariant task, for example, like the segmentation task. So in this example, we're given an input, and now again, this is just for the purpose of illustration. We have, now it's in 2 dimensions. We have like a toy example of a 2D input. And the segmentation task kind of try to identify what are the objects that, let's say, are comprising this input, and it's illustrated here with the different colors. And one prominent symmetry that I guess most of us are familiar with is, for example, is the Euclidean motion. And when it's, let's say, applied to the input scene, again, we are expecting the segmentation prediction to be invariant under this symmetry. And yeah, again, we won't go into the details, but this has already been done like years ago, and we have many examples for architectures that implement this idea very well. But if we kind of again maybe do some more closer examination, or maybe want to consider more possible symmetries, actually when think on let's say real world or no on this type of inputs, what we could actually could be also interesting to consider is that in fact there is what we can call like a piecewise Euclidean motion symmetry, where actually each object can move or undergo a different transformation. And again, we should expect that the segmentation prediction to remain invariant as well. Okay, but yeah.
Right, so we now have to know what the pieces are.
Exactly. That's the exact slide, the next slide. And of course, like modeling this symmetry is challenging. Okay, I can identify this very challenging because, as you pointed out, it requires the knowing a priori what is the underlying partition, and it's illustrated here with this curve, right? But of course, for many tasks, for example, like the segmentation task we just considered, knowing this underlying partition is, let's say, equivalent to knowing or the task that the network itself is faced with, right? So this is, in many practical settings, it's unrealistic to demand that we know what's the underlying partition. So this kind of a very immediate conclusion, or even a naive conclusion of all this short discussion, that basically in this type of settings, we can only say, or we can kind of, let's say, we can conclude that the piecewise symmetry can only be approximated. We can never know it. The network we never have this knowledge a priori for all cases. So we have to come up with some kind of notion of approximation. Okay. So again, I don't know if this slides. I don't know if it helps, but just let's go. You know, this kind of the definition of what we are used to know of what are equivariants, and let's say very roughly speaking, since this group transformation is or at least, you know, it's only approximated, we have to come up with some notion of let's say replacing this equality constraint with some notion of approximation. And in this talk, wherever, you know, some error arises from not satisfying this equality constraint accurately, I will refer to it as the equivariance approximation error. Okay, this is just a name that I call it that way. Okay, so now let's talk about previous work and actually, okay, so the previous work I'm gonna kind of present here is mostly from the computer vision literature, and it's also, let's say, updated half a year ago, but at least to my knowledge, I'm not familiar with any recent or more recent work that tackled this problem. But again, if someone knows or want to add, like, feel free to mention. But yeah, so let's start. So the first thing in terms of previous work is actually handling the case where the underlying partition is known. And of course, it's not really interesting like in the context of what we are trying to do, but it's important to mention that people come up with architectures that, let's say, already, I mean, it's very easy like to take, let's say, an equivariant backbone, right? And basically you can share it between all the underlying partitions if you know the partitions, and generate and create a piecewise equivariant network. Okay, so that's not interesting because we are, of course, interested in the more challenging settings, but of course it's important in the context of what we will try to do. The next thing is kind of, let's say, different heuristics or different models that people have come up over the years. So so there are like several options. So people have come up with ideas of, okay, what we can do. So basically the first step is to come up with some let's call it a partition prediction model. So one option would be, let's say, and it's kind of a heuristic, let's say just use, you know, a global equivariant features and use that to predict as some kind of features that somehow can basically predict, you know, for each point to which part it belongs to. Okay, but again, like if there, like it's again, there's no guarantees or no really understanding when you know, when the underlying transformation is very different from a global transformation, how would this such a model would behave in terms of the error that it introduces. So that's like one option. The second option is basically use some kind of partition prediction model, but let's base it on some local context of each point. Okay, like each point, okay, we can say it has some local neighborhood. Let's calculate this equivariant feature from this local neighborhood. But again, when this local neighborhood kind of, or imagine a settings where this local neighborhoods contains points from two different parts with respect to the ground truth partition. Okay, again, we will have some error that it's unclear how this error will let's say translate to in the language of the equivariance approximation error. Okay, so this is also something that people have done. The last thing, the last work I want to mention is a work by Deng et al., and I think it's over a year ago, and they kind of also identify all this idea of the equivariance approximation error, and they suggested an optimization process where the optimization process is based on contractive steps, right? So if you have an optimization process with contractive steps, you kind of have a guarantee that in the end it converges. However, it's not clear like what happens if the steps are non-contractive, are expanding, and then the optimization doesn't work. So kind of what we identify that is missing from previous work, in some sense, it's unclear how failures in the partition prediction model eventually affect or translate to the equivariance approximation error. And what we kind of want to ask in this work is how can we design a piecewise-E equivariant point network that is able to provide bounds on the resulting equivariance approximation error, and these bounds are kind of are controlled by elements in the design of the network itself, right? So imagine like I'm a user, I'm using, like I have the I'm a user of this architecture, and for example, I have some guarantees on the choices that I make in the architectures and how they will affect the equivariant approximation error. Yeah, so that's the goal of all of what we are trying to do here. Okay. And maybe it's a good point, like if someone has, yeah, for questions, but
yeah. Maybe maybe we can now say, right, you're not concerned with like here we're not going for approximate equivariance because we think it might be helpful or more helpful than equivariance for generalization or something like that. We're just going for approximate equivariance because it's the best we can do.
yeah, it's the best we can do. I mean, I know. Okay, so it's kind of the question is, yeah, because the underlying partition, right? It's unknown. So
Yeah.
it's like by definition we cannot define, this constraint, this equality constraint for all cases because we don't know what's the underlying partition. So we kind of we are looking for a definition that the definition itself incorporates this idea of that the symmetry itself is unknown. Because the symmetry itself depends on something that you don't know. So, right.
Yeah, and to maybe get us more excited, so to say, we've seen this toy example where this would be useful, your segmentation. What are some examples or like what is the prime application that you would advertise this for?
Yeah, that's a good question. So I think like again, like so imagine yeah, so I think like one of the nice applications that we also did in some way, it's kind of a one-shot learning. So what do I mean by that? So imagine that you are, let's say you are a robot or something like that, okay? And you have a scan of a room and you're given the labels like, at initialization, where is the chair, where is the table, or what is the chair, what is the table, what are the objects in the room. And given this information, this labeled information, right, you can train our network, right? And you are guaranteed, or at least up to the error, right? But you are guaranteed in some sense that in the future for all different configurations of this same scene, the network will be able to predict the right segmentation predictions, right? So if I compare it, for example, to simple transformation, like let's say just a global Euclidean motion, right? We would never see such transformation be kind of useful in, let's say, one-shot settings. But when you consider such a complex or more complex symmetries, right? This already can kind of allow you an interesting application of let's say, equivariance networks that we haven't seen before. So it kind of, right, we know like all of this behavior, right, of equivariant network operate better in limited data, right? So I think this kind of pushes the limit of how much let's say the regime of limited data that an equivariant network can operate on.
Yeah, and in any case, I think it's important to think about this. Maybe some people call it local equivariance, what you not call piecewise equivariance. If we're in scenarios where we, for example, let's say have a protein and in there's a local region in this protein that always would behave somewhat the same, and having local equivariance can also be or having this sort of local equivariance is maybe even more important than global equivariance. And would you say that work like frame averaging, for example, kind of misses the mark for these types of applications on, for example, proteins, maybe by only considering global equivariance? While 10 networks, for example, right, they then every local aggregation is equivariant.
Yeah. So in my opinion, like, the let's say the context the special context for which you calculate your equivariant features, okay, which kind of what this work focuses on, it's independent of the type of, let's say, architecture or layers that you use to calculate these features. So what I'm saying is that basically once you have this, let's say,
yeah, sure. But now this is about your particular work here, right? But I mean, and if we're now looking at the more general picture, if we don't even have a concrete notion of what our pieces would be, or we don't even know if there are any pieces in our data, but we know locality is important, then that we're missing out something if we're using something like frame averaging.
I agree. Yeah.
But then Denise also has a question.
Yeah, sure.
Yes, yeah, the remaining question is very simple. Do you train on static 3D data, or do you incorporate some kind of motion as well? Because like as a human, when I consider this piecewise equivariance for some objects, for example, I don't know, a metal cage and the swing inside, I need to understand what kind of material connects different partitions of the scene graph, right? If it is a metal string or if it is just a thread, it will be a very different cooperation between two partitions.
Yeah. So just like I answer the question first, and then maybe we can elaborate more on the question. So first of all, like what we assume here is that the underlying transformation is built on different pieces. Okay, so I'm not sure if that's what you refer to in your example, that kind of you have a more complex deformation, right? Like it's not different pieces that move independently, but they, I don't know, they have some regime of how they are connected, and maybe on that regime, the transformation is more complicated, maybe like humans, right? Where we are built of different pieces, right? But where the pieces are connected, it's not an exactly, let's say, rigid transformation. It's a more soft transformation. I don't know. So this is not handled in this work, and you can only think of it as kind of approximating this kind of a more complex deformations. And what you're asking is it's a very interesting question, but it's not part of it. Okay.
And yeah, the second question, but related, is just about you probably will discuss it later, about smoothness of the modeling of the entire system. So yes, in frame averaging, we'll have a problem of this non-smooth transition between local frames. And here we can use like global equivariant backbone instead of local frames. So this smoothness will be much less of a problem, right? Or not necessarily. Because still, yeah.
For this question, we don't even know what they do yet. So let's maybe get to that first.
Yeah, okay. Sorry.
Based on that, reason about what smoothness problems also there might be.
Yeah, I'll try to think of it as I present what we're trying to do. Okay. Okay. So yeah. So again, so this kind of the question. This is the goal, and let's try to kind of present how we try to address this question. Okay. So our idea is going to be built on a very simple fact, which is the following: whenever you have two symmetry groups, like G and G prime, and assume that each symmetry in G prime is also in G, then any G equivalent function is also a G prime equivalent function. So that's a very simple fact, and let's see how this can play the role in our case. Yeah, so consider the following example. So imagine now that this is the inputs, and and in each point here, we also illustrate some equivalent feature, some point equivalent feature, and this is illustrated with the point arrows. And consider a scenario where actually this equivalent point features were a result of a piecewise equivariant function, where the pieces are defined according to the colors that you see in the middle column. Okay, so this is kind of an illustration. And since these colors induce a partition, a subpartition of the grant with partition, which is only contains 3 parts, okay? But since this subpartition is good in the sense that all parts are let's say a kind of a subpartition of the grant with one, we can expect in such case the equivalent features will remain will behave in an equivalent fashion. Okay, so this exactly is the translation of what you see above, this simple fact to the, let's say, to the piecewise scenario. But whenever we kind of in a case, but this function were actually defined with respect to a bed subpartition, that is, it contains at least one part that has points mixed from 2 different parts in the grant with partition, then we will have some errors that are unpredictable. Okay, so I'll use this language of a good subpartition and bad subpartition. Okay, but this very simple fact can be already utilized in a very, let's say, naive way, but it can be useful. And so what do I mean by that? I mean, we can do the following. Okay, we can we can use some kind of a probabilistic model for a partition prediction that kind of detaches us from the inputs. And we're going to do it in the following way. We're going to just draw a random partition, which, let's say, to make it just more, let's say, to exclude some non-interesting cases, let's just use the distribution of non-degenerate partitions of some size k. Okay, so for example, I'm a user now of this model, and I choose some number k, which basically tells you how many parts I'm going to have in my partition. And now my model for partition prediction is just a random partition from this all possible partitions. So this seems to be very naive, but it has the advantage of where we can kind of address this equivariance approximation error solely by the probability of drawing a bad partition. Okay, it kind of gives us the freedom of not, let's say, we don't have to handle the function itself, or let's say some properties of the function itself, of the model function itself. I mean, the entire error can be naively bounded just by this probability model. And the last thing, which is, let's say, an appealing property, is that it has some kind of a desired limiting behavior, in the sense where as you increase k, right, this probability will decrease to 0. So in a sense that we can, you know, again, as some kind of a user of this design, a user can increase k, and you can imagine, you know, how this graph behaves. When I mean the graph of the probability to draw a bad subpartition as a function of k, right? As k increases, this probability goes to 0. basically, so in the end, you will have zero equivariance approximation error. But of course, this is not really a useful model, right? It kind of already maybe identifies the kind of a trade-off or a fundamental trade-off that we have in this type of models, where kind of as we increase this number of possible partitions, right, that our function needs to be piecewise equivalent with respect to, this will immediately reduce the expressivity of this model, right? And this warning is especially relevant, right, to how we design piecewise equivalent networks, where we take a shared backbone, right? And this shared backbone is applied to each part individually. So let's again take this limiting behavior where each point belongs to a different part, right? And we have a shared backbone. So what would be the only function that our model can let's say express? It's just a constant function. Okay, so I mean, let's say again by construction we see that we have this limitation, right? Where in some sense we would like to use a large K because we would like to reduce the equivariance approximation error. But if we're going to use always the same K or always use large Ks, we will have, let's say, non-expressive models. So we need to come up with a way to overcome this challenge, or let's say one of the first challenges we need to address. Okay, so this is the idea, and the idea is again, let's say, follows. Let's say the network design paradigm, where what we're going to do is a compositional network architecture, where the idea is to first, again, you can imagine that we have this K, or the number of partitions, but now we want the complexity of each partition to decrease such that we can gradually be able to express or model more functions as we advance in the layers of the network. And the way we're going to do it is that each layer is you can think of it as like a piecewise equivalent function, but you can imagine that it not only predicts point features like every equivalent function does, but it also predicts, let's say, a special equivalent feature, which going to be used to parameterize the partition prediction of the next layer. Okay, so that's what it's shown in this illustration. Again, like the arrows illustrate this first feature or special feature, equivalent feature. Again, it's the arrows. What's this equivalent feature is? It's illustrated with this arrow, and you can imagine if, for example, in this part, right, since these arrows are close in some sense in space, this parameterize a partition in the next layer such that these points have merged to one part and generate a coarser partition. So that's the general idea. And again, this is kind of composed through multiple layers in the network. Just to give usually like people ask me, okay, in practice, how many layers usually you employed in the experiment? So in our experiments, we had 4 layers. And basically that's the kind of hyperparameter that we choose. Just comment about the end when we're gonna follow. I mean, we're gonna cover the experiments. I'm just giving this detail already now. Okay, so this is the general idea, but there are, of course, yeah.
We'll get into more details about this.
Yeah. This is just from here. It's really hard to understand. I mean, how, of course, this is done. But what I'm gonna say, just this is the general idea of how you're gonna overcome this. Let's say this idea of, okay, you want to start with a very complex partitions, and gradually you want to reduce their complexity by merging different parts. That's the idea, and this introduces several challenges. But the main challenge is, again, like how do you define this, or how do you do this parameterization? That's one. And the second, I'll give you, and the second question is of course, how, okay, even we have this idea, how are we going to control this equivalence approximation? Or I haven't said anything about it. Right? Yeah. You have another question? Or...
If we were to start with one partition being 1 point, right? Or
yeah.
one, then we would have no problem in terms of not being able to express everything. But this is maybe not the best thing. So you now start grouping these together, and you always group together. You never ungroup, right?
You never ungroup. Yeah, it's like bottom up, I think.
Yeah,
and that's the way to look at it.
What's your starting partition?
So yeah, so the starting partition, it has like in the architecture, you define how many parts you're gonna have, right? So imagine like, let's say, that's also what, let's say k equals 64, whatever. And it also be, I'll go over more details, and it's very important how you start. The way you start is from this, let's say, naive partition prediction model of drawing a random partition model. Okay, this is very, let's say, fundamental to the method. I'll explain in a second, because it also will be related to how we're gonna bound this error, this equivalence approximation error. Yeah.
Sounds good.
Yeah. So I'm gonna refer to the partition now. We're gonna use again like a probabilistic language, and just gonna call it Q. Q is basically this measure that is going to be used to draw partitions. So whenever I use Q, that means that this is the result of a network. But basically, this is parameterized by networks, by network prediction. And whenever I use Q simple, that's basically this what we call like this simple partition prediction model that does not depend on any parameter. It's just a uniform draw of a random partition. Okay, so we have the idea, but now we kind of need to join the elements together and understand how, given this model for Q, how can this be used to control an equivalence approximation? Okay, so again, we start like the way I'm covering is kind of we're starting from a bird's eye view, and as we go, we're gonna zoom in to more details, but it's still from a bird's eye view a bit. But again, now the very fundamental idea I want to introduce is, okay, let's say, imagine now that you have a model for Q, right? You have some model for partition prediction. And now the question is, how do you connect this model to the equivalence approximation? And the fundamental idea that we suggested, again, this is purely a suggestion, okay, but there's a lot of freedom here. This is a suggestion, and it will be very, very interesting to discuss this or come up with different suggestions. But what we suggest is the following, is that for a partition prediction model like Q, as the model itself become more certain in its prediction, the constraint that we have on this model is that the probability to draw a bad partition basically a partition like we defined before. It's like a partition that contains some part where we cannot control the Equivariance approximation error. So we want this probability to be no worse than the one of this simple model of the uniform model. Okay, so this constraint can basically give us a way to connect a general partition prediction model like Q, okay, with the basic one. Okay, so you can imagine now, again, I'm a user of this architecture, and let's say I have some hyperparameter where I control Q, and the hyperparameter tells the model for Q how much certain Q should be in its prediction. Okay, let's say, and again, as this hyperparameter kind of controls Q to be more and more certain, basically Q would basically constraining Q to produce this the partition in the same way. Let's say you have some algorithm how you want to predict this partition. What we suggest, again, which is kind of naive, but at least we want it to be not worse than the simple model. Okay, this kind of gives us the hint that we're going to use this in order to bound the equivariance approximation. Okay, this is going to be a naive bound on the equivariance approximation error, which will be solely in terms of the probability of drawing a bad partition. Okay, so this is the general idea about the Q model. Okay, so to summarize again from the bird's eye view about again, I'm gonna again place us where we are at the story. So the story is that we want to build a network architecture, right? And in each layer, in addition to predicting equivariant features, we also want to predict a partition prediction model, what we call a Q. We call it by the name Q, and Q is kind of a probability over the possible partitions. And the previous slide, we identified some characterization of how that will enable us to bound the equivariance approximation error. Basically, we don't want it to be worse than the simple model. Okay, that's a naive characterization, or at least that's the best thing we can do now. And the other conditions are relate, let's say, are more technical in the sense that one, of course, it needs to be differentiable. We want to incorporate it into network. And the last thing is that the optimization is feasible in the sense that it's kind of a discrete optimization problem, right? It has many, let's say the space of optimization is huge, right? And then we want to come up with some good approximation just to make this optimization feasible. So these are the conditions about the Q prediction. Okay, so and now this leads us to some sorts of a definition that will support the idea for a layer, let's say a piecewise equivariant layer. And this is the following definition. Okay, so I'll try to decompose this definition slowly, and let's start understanding it. So, so first of all, this definition depends on Q. Okay, so you can imagine like a layer gets a Q partition prediction model as an input, and we want to consider for each layer all the possible functions that satisfy this definition. So first of all, like we see that this is kind of the replacement to the equality constraint, right? We just want to consider this norm differences between your transformations on the input, right? To respect the transformations on the output. That's the second comment. The last comment is that we are considering functions which are, let's say these functions H are functions of let's say, they don't know anything about the partition, right? They are just, let's say, we denote the input x. X, you can think of it as a scene, right, or as a point cloud, or as a set of points in R3. And the function h does not know anything about a partition, right? So it kind of, you can think of it as it has some kind of a marginalization happening over there, or let's say the way we're going to support this model is going to be through marginalization. That's another comment. And the last thing is that we want to bound this error in this definition we suggest by two terms. Okay, the first term, what I mark here, this is just a probability of drawing a bad subpartition under the simple model. Okay, so this is independent of Q. This is kind of a, again, it only depends on K, right? You can choose K to be very large if you want to decrease this probability to 0, right? But it's always going to be there unless K is equal to the number of points, K equal to N. Okay, so this kind of, we cannot do better than that. And the second term is the uncertainty measure on Q, okay? In the sense that Q has, again, these hyperparameters, some hyperparameters that control how, let's say, how, let's say, control the variance in the prediction of the partition by Q, right? And the requirement, as I mentioned in the previous slide, is that this function goes to 0, right? This delta of Q, the uncertainty in Q go to 0. Let's say you are very certain. So very certain this goes to 0. What we are guaranteed is that the lambda of Q, okay, is going to be no worse than Q simple, the lambda of Q simple. Basically, the probability of drawing a bad partition. That's, let's say, the translation of what I said in the previous slide to how we can formulate. So there are some conditions on delta of Q, of how you parameterize Q. Okay, and M is just a bound. Okay, it's like a bound on the function H. Okay, so this is the definition for piecewise equivariant functions that we want to that we advocate for. And the second thing is, of course, to come up with a model that supports this definition. And again, let's see what's the idea here. So the idea here is as it's built on the following. So first, you incorporate, like I mentioned in the beginning, some shared equivariant backbone. Okay, so this is psi. And the way it works is that you can is the following. So again, X is the input, and you can think of a Z, right? Z is some partition prediction. Okay, Z denotes a partition prediction. And the way we evaluate this function, right, is that Z kind of masks out, right, for each part, right? And then we apply psi on it. That's how this model works. So this is so up to here, this is very standard. I think that's how anyone would kind of implement this kind of piecewise equivariant function, right? What's more interesting here is the way we marginalize over the possible Z that we can draw from Q. Okay, and the way we do that is by basically choosing for each point you choose its part by the one that has the maximum. Okay, like in each point belongs to the part where the probability is maximal. And this will give us, let's say, the tools in order to bound this, using this marginalization scheme. This will give us the right tools in order to bound this or to show that this function h satisfies this this bounds. Okay, so you could come up with different marginalization schemes for z, right? So imagine again you have some q, some partition prediction, right? And now you draw z, which is a partition from this underlying probability, right? For example, I could marginalize this by taking the expectation, right? Maybe over z, right? Or I could take the expectation over the entire function, right? I could have let's see if I can write here. No, sorry. Yeah, I could have, I don't know, I could have done something like that. I don't know, define some h, right? I don't know, z drawn from q, right? I could have done something like that, or I could have done maybe something like that, h of x. Yeah, so maybe you could have done something like that. Could have come with different marginalization schemes, right? But in order to support this idea, actually we come up with this scheme.
Okay.
So, yeah.
Can I have a quick recap? So,
Yeah.
our Q is a distribution of partitions given given some input or given some X. And
Yeah.
how does this Q work? Is it another neural network?
Yeah. So I mean, in Q itself, in the end, right? It just a list of numbers, right? At the end, Q is a list of numbers for each point, right? What's the probability? It's a matrix, right? Q is a matrix.
Okay.
Okay, Q is just a
for
matrix.
belonging to a certain partition for each point. So it's basically we have n points and we have k partitions, so it's an n by k matrix.
Yeah, exactly. Yeah.
Okay. And then so we draw a partition from this matrix, and
Yeah.
this also this partition can be predicted by a neural network or by one of your layers.
Yeah. Yeah.
And then we can draw from this partition distribution, and we can also estimate the results of the partition distribution when putting it into the next layer by like taking your first expectation or taking your second expectation. Yeah.
Yeah. I think I just want to say like exactly what you said, and I'm just going to repeat what so first of all, Q it's just like, I don't know, it's like a list of numbers and by k, right? And you can think of it, I don't know, like, and in each we have like Q1 up to Qk, sum of Qi j equal 1, right? This is 1, k, right? And each Qij is larger than 0. That's kind of, and you can think of how, and again, I didn't say how Q is parameterized by network, right? For example, let's say the most naive way to do that, right, is do some kind of softmax, right? For each point, I know this is my prediction, right? This is the most naive way to do that. But this won't work, like from experience. I'll just I'll go over it later on, okay? But you can think of how to do that. But that's one thing, and the other thing is and the last comment I want to say that what I wrote here about different marginalization scheme, that what I claim that with these schemes you cannot get this bound. I mean, it's not clear to me. I mean, how you can bound the equivariance approximation error using these schemes. It's not. I mean, it's not clear how to do that, but with this scheme, it's very simple to do that. I mean, that's what I wanted to say.
So you check take the argmax over J. So
yes.
what
So
does
how
J?
does this work? Yeah. So basically, yeah, you need to come up, right? Like you need to come up with a partition. So what's the algorithm that this scheme tells you how to do that, right? You go for each point. You look what is the maximal Q, let's say for the point I, what is the maximal Qij? What's the maximal in what J it falls, right? And given that J, that would be the part that these points belong to.
Yes. Yeah, clear.
Okay. Yeah, I mean, and intuitively to understand why does it, let's say, more easy to work with when you try to bound this quant's approximation error, in the sense that, right, like each time, let's imagine like each time you, or the way I'm going to see it, like, so, okay, so given the partition, okay, given this Z that you draw using this algorithm that I just described, okay? So imagine that this is the Z that you have, okay? So under this partition, right, your function evaluations with regard to this partition would be the same. And the only error is going to be, if you have any error, it's going to be a result of the fact that this partition is not a good subpartition, which is going to be, let's say, encapsulated in this term. Okay? Whereas if you use some other type of marginalization, let's say this type of marginalization, okay, let's say take the partitions, right, and basically take the expectation of each point to which partition it belongs to, right? So this is very non-geometric transformation, right? Like you can imagine it uses, what is the expectation of this? Basically, it takes some number between 0 to 1, right? So this kind of a transformation is kind of a scaling transformation, and it's not clear how networks that are, let's say, applied on this type of transformation would behave in terms of their error, right? I mean, you could come up with different types of requirements, right? But at least it feels that it's more complicated. Yeah, so that's the idea here. Yeah. Okay, so the last technical issue that is not covered in the slide is how actually we do this parameterization for Q. And the question is, maybe we should go over the experiments first and then go back to it because it's more technical, I think. That's but I don't know.
Maybe right. We want to understand the method completely.
Okay. So let's talk about let's
what
talk
you're
more.
doing to achieve the results, and that's maybe like okay, maybe the how do you bound the error and so on. We can talk about later, but I think like how
I agree with you. I agree with you. Yeah. Let's cover the details of how you parameterize Q. Yeah. So I didn't have like I'm gonna maybe share now I'm gonna exit it for a second.
So my question sort of would be, how do we start? What is the starting partition? Then how do you predict the Q in the next round? And is next Q prediction influenced by the previous Q prediction other than through just partitioning the stuff? Yeah, stuff like that.
Yeah, I understand the questions. Yeah. So okay, so now let's cover how we do this Q prediction. I'm gonna do it from here. So again, so the way we suggested to do that is the following. So first, as I mentioned before, so when you think about this Q prediction, right? This is an invariant feature in the end, right? This for like under the ground truth, or let's say under the ground truth symmetry that we don't know. Again, this is kind of an invariant feature. And I already said that maybe, you know, you can think of a way to do that is maybe by doing some kind of a softmax, let's say a partition. But also in practice, like from what I tried, this doesn't work, and I attribute it mostly to the fact that there are many, like the optimization is very, it's too complex. Let's say if you use a softmax, for example, right? For a softmax, there is, like, if you think about, let's say you have k parts, right? So for softmax, there is the first part, the second part, the third part, and the k part. Like each part has an order, right? And we kind of would like to reduce this constraint, right? I mean, we don't care if, let's say, all of these points, let's say, that belong to this part are actually in the first part or in the second or in the k part, whatever part it is, right? So softmax by construction has this over limitation, and it complicates the optimization process. So what? So in order to handle that, we suggested the following is, and this is done in the following way. So in each layer, right, what we predict is an equivalent per point prediction. Okay, this is, let's call it Y, and this is exactly like the arrows that we saw in the slides before. And now we want basically do some kind of a clustering or a differentiable clustering operation where we assign each of these Y's to some cluster centers, and the natural way to do that is to use what we use here is a Gaussian kind of a Gaussian mixture model energy. This is equation 9, where in the end, the way these centers are selected is by some sort of an inner optimization problem, right? This is kind of what you do in the as part of the layer, right? You do some, in practical sense, what you do is you do some steps of EM algorithm, and you find these centers, these mu I star centers, in order to assign these point features to the right clusters. And another important here, and in difference, let's say, from the regular, let's say, Gaussian mixture model that we might be familiar with, is that we have an extra parameter, which is an hyperparameter of the architecture, which is the density of each Gaussian. Okay, so let's say we have k Gaussians, but the density is set a priori. This is hyperparameter for the architecture. Okay. And exactly this this parameter exactly will enable us to control how much this Q prediction model is certain in its prediction, right? And moreover, where it has this behavior where sigma goes to 0, right? Or this hyperparameter is very, very low. Basically, this whole model is equivalent to doing a simple prediction model, which is basically drawing a random prediction model, because when sigma is very, very low, each choice of mu star will behave as a local minimum of the energy 9. Okay, so basically we get that's how we can get this behavior that we are looking for by actually using this hyperparameter sigma of the Gaussians to be fixed, right? And this hyperparameter as it goes to 0, has the right behavior that we are looking for. The last technical details, the technical detail that is important here is how we make this process differentiable. Why? Because we have like an argmin prediction, and the way we did it in this work is that we use implicit differentiation techniques, right? And we didn't we didn't unfold this step as part of the computational graph. We just you find the minimum outside of the computational graph of the network. Once you have the optimal mu star and pi star, what you do is use implicit differentiation techniques to make this prediction differentiable in the network parameters, which are a prediction, which is y. In the end, this is very simple. Like I can show you the algorithm. It's what you do. It's what you do here. Like once you have this mu star and like pi star, like the optimal centers, you make them differentiable in the parameters by basically multiplying them with this I matrix, which is the Fisher information score matrix. I mean, this is kind of a technical detail that, but it's not that complicated, like to implement it. But I mean, you can verify that now you have the right derivatives, the first order derivatives that you're looking for. Yeah. So this is kind of how you do this. This is how you do the Q prediction.
Just a quick query here. So mu is the negative log likelihood hook of the GMM, the Gaussian mixture models here?
Mu is the centers of the
okay. Okay.
Yeah, mu are the centers, and pi are the prior probability of each point to belong to center j, pi j.
And where is softmax showing up here again? Is it being plugged into equation 10 or?
Sorry, can you please repeat the question?
I said, where is softmax being plugged in?
I mean, so there's no like so there's no softmax here, but you can look at this equation. This is in the end, right? Like it's very similar to softmax. This equation 10, but this is the equation 10 is the optimal assignment of or basically how you calculate this Qij in the Gaussian mixture model. But this is exactly like softmax.
If I could ask a quick question, could I ask my question?
Yeah, sure.
Yeah.
Yeah. Thank you. Thank you for the presentation. I see below the network architecture, so I just want to ask a quick question about the network architecture. Please forgive me if we've already discussed it. Yeah.
Sure.
Yeah.
Are you asking what's the network architecture?
Yes.
Yeah, okay.
Would you be able to briefly describe? I know we're much over time. I just wanted to ask. Can you just briefly describe network architecture?
No, no
I'm
worries
just curious
about being over time or anything like that, right? And if any of you have questions, you can just ask questions. You don't have to ask if you can ask a question or if you can ask a question or such. Just go ahead.
Yeah.
All good.
So again, so what we're presenting here, I feel it's orthogonal to which choice of architecture you actually choose. But just to give, like basically what you do is what you see here. You take an equivariant backbone, let's say a Euclidean equivariant backbone. It can be tensor field networks, it can be vector neurons, it can be frame averaging, your preferred choice. And you take this equivariant backbone and you apply it to each part that you see here. I mean, you take the same equivariant backbone and you apply it to each part that you see here, a shared part.
I see.
Okay.
I see.
And this is in terms of let's say formally written here in equation 8. Psi of B is the shared backbone, and you can think of this as kind of a masking. You take the input, and for each J, which is a different part, you mask out different parts of X, and you apply psi on it. And the way you combine it back to be an output is by applying again this masking.
I see.
Yeah.
Thank
But
you.
psi can be any network that you want to come up with, at least as long as it's an ED equivalent backbone.
All right, thank you.
Sure. Okay, so yeah, so this is the Q prediction. I'll go over now on the experiment.
Sorry, can I very quickly ask?
Yeah.
So the hyperparameter K, the initial number of partitions.
Yeah.
Yeah, I lost it for a little bit. How do you set it? Is it some? So is it also optimized or not?
No, it's not optimized. It's an hyperparameter. I mean, from experience, like I didn't play with it too much. Like I said, I think K equals 64. It does, like, of course. Okay, so I just want to give some limitation. Of course, you can think of this K also as kind of a bet size. Like you can't really, let's say you have inputs of 20,000 points. So I don't know. Oh, right. So like you can have K equal 20,000. It won't work. Just in terms it doesn't fit memory. I mean, so that's like, so there is like this just practical limitation. I do want to, so it was fixed. It was, I don't know, set K equals 64, and it was good enough for all the experiments that we did in this paper. I do want to make another comment here, is that we did do kind of a sparse implementation of this shared backbone, right? Again, like if you look at the formula, if you look at the formula for the network, right? Again, show the formula. It's what you see here, right? Like the formula is that we have this X, right? And each time we have a different part that we want to apply the shared backbone on it. We can't have the shared backbone being applied to all points at once. I mean, it's redundant, right? Like we have many points that go to 0 or something like that. So in order to make it efficient, we did like a sparse implementation of this architecture, and that this was crucial for us to use a large K and doing it on large inputs. So that's another comment I wanted to mention. Okay, so let's go. Yeah, now let's talk about the experiments. So the first experiment, we considered a data set of human body scans. So in this experiment, we use our network in settings where you have, let's say, lots of data. You want to train it on the data set. It's not like the one-shot example I described in the beginning. And we utilize the data set to test our method in different settings. So we considered different splits. So the first one is just a random split. Okay, you have human body scans in different poses. You just do a random split. And the goal of this test is basically to see if your method, if our method maybe has some, okay, maybe we generalize in, you know, in some interesting settings when we have like complex deformation that you didn't see in the training set, but maybe we are introducing some trade-off and reduce, again, the expressivity of our network. So what you want to do, you want to take best, you know, the best point networks that are out there in terms of expressivity. You want to see if you perform at least as good as those networks on a random split. So that's the first test. The second test is that we divided the train test split by a random choice of a different action from each human. Okay, so the question is, for example, imagine, let's say, in this asset you have 10 subjects. So you take, let's say, arms up pose and exclude it from the training set from the first human and move it to the test set. But the second human does have this, this movement. So again, you want to see if the network itself can generalize movements from other humans, or maybe the baseline can do that better than what we do. Okay, so that's the second test, and the third is split is where we take a specific movement. I think we took in this case the one leg jump, and exclude it from all humans in the dataset, from the training set. So the network, in our case and also in the baseline, has never seen a human raises its leg. Okay, so this is the third test. Okay, so here are some quantitative results on the segmentation of human body scans. I guess the numbers not really interesting, except for the fact that we do better. So we did also use some local context equivariant feature. This is the APEN method. Okay, so I think that's a very interesting comparison. And also, let's say, global Euclidean networks like vector neural, FM averaging, and even those that don't incorporate any Euclidean motion prior into the design. And on all of these different splits, we perform better. Let's look at some qualitative results. 1 second. Yeah, so again, you can see for the one leg jump example that I've been talking about, again, you can see how our method is pretty much consistent. It's pretty close to the ground truth. This is just a random choice from the test set. Okay, so this is for the humans experiment. The second experiment I want to talk about is exactly the experiment I described in the beginning, which is the one-shot generalization, where we took a real-world room scans, and each room is captured in different timestamps, where a long time objects in the scene in the room have moved. They are positioned differently. And we test versus methods that trained on a large-scale synthetic data set. Again, from the number, we tested on 8 scenes, on 7 of 8 of them we did better than the synthetic one. And I think it's interesting to look at the qualitative examples. So here, for example, at the bottom, we see a comparison to the method that was trained on a large synthetic data set. And you see our method is stable, when you have even this large deformation, where the screen suddenly is on top of this desk, and how the baseline collapses in this type of examples. And also I want to mention that this is a real-world room scan. You can see the deformations between different configurations are not just the rigid movements. So there's a lot of noise in this problem. And it's interesting how just from one shot, our method is pretty robust to this noise. Okay, because I mean, when you have a room scan and the sensor, I mean, there's just noise in the sensor, and it depends on the directions that the sensor was capturing the inputs. And if you look up more closely, you can see there's a lot of differences between different timestamps. Even that our method is pretty stable. Yeah. So I think I can summarize now. So in this work, we mostly tried segmentation, classification tasks, where we applied our backbone. From our experience, it showed superior generalization over the baseline that we compared to. In terms of future work, so one thing is I feel that, and I think I also mentioned it a bit, like, so first of all, many of the bounds are naive in some sense. I felt like it's a first step, and maybe we can come up with different bounds or different, let's say, probabilistic models on how you would approach this problem, or at least even the probabilistic approach of how you bound this approximation error is just one way to go. I think perhaps there are other ways to go. So I feel like it's in the beginning of maybe trying to control this equivalence approximation error, and maybe do that in a let's say in an analytic way, how you would approach this problem. The second thing is that we also been trying to play with is also tackle other tasks, perhaps generative modeling, which is a very popular task nowadays, or maybe reconstruction. So this is a very strong prior in 3D that we feel it would be interesting to use this prior. Yeah, thank you very much.
All right, I can also say thank you, and yeah, thanks for answering some questions, and I enjoyed it a lot. I guess I had this maybe overarching question at the beginning, that's about approximate equivariance in general. How familiar are you? Like right here, we have the scenario of we want to do something and we can't do it equivariantly, so we resort to approximate equivariance. And
Yeah.
But we've seen also other papers arguing for a value of approximate equivariance as opposed to complete equivariance in situations where we could have complete equivariance. And just because then we can maybe build different networks, we can have different training dynamics, right? And not all that matters is the expressivity and the generalization that you have with the perfect network, but it also matters like how easy is your network to optimize, and then how well you generalize after taking that into consideration, things like that. So what would you say is maybe the most canonical work or the most canonical papers to look at for if we further want to explore these directions?
Yeah. I will be honest, and I think I'm not the right person to answer this question.
Okay.
Again, like I think, yeah, you can the word approximation here is general, and like you described, can serve in different settings. I think in equivariance. I think also one more thing that I can, or let's say one more aspect of approximation that you didn't mention, that I think there are some works that do, is also when they say that in test time, even the symmetry is not correct. Right? Like I mean, you expect the inputs to not to behave in a way that the model assumed with respect to the underlying symmetry. So that's another type of errors that or some cases where you don't know the symmetry. Yeah, but yeah. So I know, like, so maybe there's overused the word approximately equivariance. It's been used in different settings, and I'm not sure about the relation between all of them.
Yeah.
Yeah. So yeah, I feel like yeah. So again, like in these specific settings where mostly the error arises from what I call the partition prediction model, I haven't found a lot of literature addressing this problem, and that's exactly, I mean, so most of them were kind of, let's say, handling it from a practical standpoint of just what can you do, you know, or what algorithm can you suggest in such settings. And I think the theoretical side of how to approach this problem is very unaddressed in the literature. And if it is related to some of the works that you mentioned, so now honestly I say I don't know, and I'm not the guy to answer this question, but it's sure is an interesting research question.
Yeah. Okay, well then we have some more questions, and like if we have more questions, right, then please don't go, thank you so much for the talk, and so on and so on and so on. Can I ask a question? Just ask. Let's go. Denise.
All right. So I still have to ask about this K, because it seems that the method looks kind of like a soft version of K-means in some sense, and then you will possibly run in some problems with if K is mismatched from the real distribution in the scene. But from your examples, I don't see a lot of subpartitions, so maybe I just don't understand, and this K can eventually just go away, and you do not have to keep this number of partitions, right? You can end up with just 2, for example.
I mean, the expected behavior or the good behavior, again, these partitions are learned from the data, right? There's no miracle happening here in some sense. There is, okay, but the expected behavior is that, or what the network encourages is that you always start from this simple model, which always going to use the full capacity of K, will always have, let's say, 64 parts, whatever K it is. And the partition prediction model is encouraged by the energy and by its hyperparameters to be a coarsened version of the previous layer. Okay, I can show you an example.
Okay, I get it.
Okay, like this is from a real example appendix, right? This is like example of the partitions, right?
Yes.
How they become
This is really cool. And then the second question is more of a far-fetched side, but it seems that in some way this partitioning approach, like for me, it looks a bit similar to those algorithms for isomorphic subgraph matching, like LUX or Babai algorithm. Of course, they are much more discrete, and they are not approximate. So for this reason, they're not that much similar, but it seems that maybe it can be also useful for something like large graphs, not just point clouds, for approximate equivariance of subgraphs. Or do you think that it's too far-fetched because the graphs are too discrete and it would be rather useless, even for large graphs?
Again, I'll take the honest approach and say that I don't know.